This is the Bayesian alternative to a one-sample t-test. First of all, we need to define the parameter of interest. And the parameter of interest in the alternative to one-sample t-test is what we call the population effect size, and we call that delta. We use the Greek letter delta. And delta is calculated by subtracting a mean mu 0, from another mean, mu 1, and then dividing that by the standard deviation. So what are these two means? In this case, mu 1 is a mean that we are going to estimate with our sample. And mu 0 is a specific value, a value that we specified. So we want to compare the mean of our sample with a value we specify before running the analysis. Examples of this is, let's say we want to collect data on an IQ test in a sample, and we want to know whether our sample is higher or lower or the same as the mean IQ of the population. And we know that the mean IQ of a population is typically 100 because the IQ test is standardized for the mean to be 100. So we may decide to compare whether our sample is higher, lower, or the same as the one in the population. So that is the typical case of the one sample t-test, and here the Bayesian alternative. Okay, so we've got when we collect data, we are going to collect data on whatever numerical variable we measure in our sample, and then we are going to obtain the mean, and that's shown as x bar 1. That's the mean of our sample, and then we are going to subtract the mean 0, which is the specified value. And because we don't have the standard deviation of the population, we are going to use the standard deviation of our sample S to calculate the sample effect size. So the data in our study, in this case, would be the Cohen's d, and we need another component to do the analysis, which is the degrees of freedom, and the degrees of freedom in this case would be the sample size minus 1. Okay, so what are the priors? And again, as in the model comparison approach that we did in other Bayesian analyses, we have a null model and an alternative model. So in the null model, we need to put a prior on the parameter of interest, which is the delta parameter. Well, in the null model, there is no distribution, or we can say that we've got a spike on the value that we specify, or we can say that delta equals that value. It's the same. And in the alternative model, we use the Cauchy distribution with a scale parameter of 0.707, which is the default parameter that JASP uses, so we just use that. And again, it is a symmetric distribution around 0, and so in which values that close to 0 are more likely and far from 0 are less likely, so similar conceptually to a normal distribution. The likelihood is a t distribution. So basically, what typically what JASP does is to calculate a t-test on the sample. So I'm not going to explain the t-test in the sample because that's you've seen that in many other courses, so we are not going to go through that. So basically, the likelihood is what's the probability of obtaining the t-test that we obtain in our sample, given that the population parameter is a specific value, and we've got a number of degrees of freedom. And again, degrees of freedom is the sample size minus 1. For the alternative model, is the same, with the difference that delta is not going to be a specified value. We are going to use all the values that we allowed delta to have in the prior. So for each of these values, there will be a t distribution. Okay, so that is the way we specify our one sample t-test Bayesian alternative. Let's go through an example. And this example, I'm using a sleep dataset. This is a fake dataset. And we've got a control group. So basically, this is a group of participants who have sleeping difficulties, and they were randomly assigned to a control group or to an intervention group. And then we measure the number of hours of sleep, or the average hours of sleep per night after the intervention. Now, before doing the comparison between the groups, and we are going to see that in the independent samples t-test Bayesian alternative, we are going to see whether our control group is a sort of representative of the population. And how do we do that? We know we've got our cable data, which says that people with sleeping difficulties, the average number of hours per week of sleep per week is 5. And again, this is all fake data. It's not something that I'm claiming this is the case. So we want to see whether our control group, the mean sleeping hours, is similar or different than that specified value. So in our data set, the mean of sleeping hours in the control group is 4.996, so very, very close to 5. The standard deviation is 1.205. So we've got here the graph of the posterior distribution of the alternative model. And so we've got the prior distribution, which is the Cauchy distribution with 0.707. And then the posterior distribution that is more concentrated around 0. So we've got here the median of that distribution, minus 0.003, and the 95% credible interval, which goes from minus 0.195 to 0.190. So basically, it's an interval around 0. And the Bayes factor says that the Bayes factor 0.1 is 9.028, which means that the marginal likelihood of the model of the null hypothesis is 9 times higher than the marginal likelihood of the model with the alternative hypothesis. So therefore, this says that it gives us confidence on the null hypothesis, it's evidence in favor of the null hypothesis, and so we can be sure that our control group is representative of that population.